Hello YouTube. I have made something that I wanted to show you. It's a project I've been working on for a very long time. I've been having a lot of trouble making it. I have made a redstone computer in Minecraft. This is done in the Bedrock edition. When a word decides to load up, I will show you here. So yeah, this thing is fully finished. And it's a pretty big mess, but hey, trust me, it works. Ladies and gentlemen, I present to you the Twin Ducks redstone computer in Minecraft. It's a 2-bit system, which means it has 2 bits of data, with the exception of a 4-bit instruction system to allow up to 16 instructions. As you can see, this here is using the old style of making the control lines. The old style was much more easier to make than the new style. And I'm going to show you how to program this and show you how it works after I explain some backstory. So I've been trying to make a good redstone computer in Minecraft forever, making some pretty basic stuff. I am not the best at redstone, of course, but I'm trying my best over here. And it's taken a while, and I've been struggling a lot. There was not much information online about certain things I need to use, but eventually I got some things and I just winged it. So here we have this here is the horizontal design, finished and fully working. Although it's a bit of a wire salad over here, a little messy, it worked perfectly fine. I tried to make the vertical version that everyone else seems to like to make, but the problem is making the instruction system. Like, how do you do that? It's like, nobody ever makes a video that shares their info. Like, I want to know how to make a vertical instruction decoder and instruction set, like in assembly language, but nobody seems to know how to show that or want to show it. Everybody is so, like, secretive about it or whatever. I tried to do this, but I couldn't get the thing to work efficiently. So I stuck with this design right here, the old-fashioned horizontal design, using the torch mechanism. Now I'm gonna show you this thing working. The current code I have programmed onto this is it will read the user input, write it to the display, then check to make sure your value is equal to 3. Let me power on the computer right now, and you will see. Hang on, let me just turn down the music, the volume, in case music's not to play, and like turn that off. Now, it is currently not going to display anything, but it's running on here. And it repeatedly reads the input, displays it, and checks if the value from the ALU is equal to 3. So let me just type in a number. It will eventually cycle back, read my number, write it to the display, and then it will check to see if this value equal to 3. I put another 1 in there, it will say 2. See the display updated when I got to that part? And now, let me set it to 3. It will update on the display up here, and then it will stop the program from running, because the number is equal to 3. I can turn these off on here, it will not update the display any longer, because the program has stopped from the halt command. Now I'm going to show you how to program this. So here's what you got to do. This defaults to the first line, so I recommend avoid using the first line. You technically only get 15 instructions with this design, unfortunately. But it's a consequence to pay for this thing being extremely basic, basically. So I'm going to erase all these torches on here, so I can show you how to program this. And some people may already know this, but in case you don't know how to program computers like this, I will show you how to. So, let's make a program that just adds 2 plus 2 and displays it to the display. But unfortunately, it will not display. As it's a 2-bit system, it can only go to the number 3. This will need me to take into account the overflow function, which I do not have. Actually, instead I'm just going to make it say 1 plus 1, because it will say 2. So here's how you program this. Read these. First, you gotta see how big you want your program to be. My program will be approximately 4 lines long, 5 if you include the one we're not using, so 4 lines long. Here is our address. This here is our command line address. We just fit it in a binary fashion. This here is a 1. Want it to go to 2 on the next line. And it will go to 2. Then you say 3 and 4. This here is all the lines we will need for this this thing to work on here. We have our code address set out. And now what we want to do is tell the computer we want to put a 1. We have a force bit on here, which is basically the load store value function. We set this to 1 on this line. We do the same for the next line. Then over here, we want to write it to the ALU registers. We start with register A, then we set register B. On the last line over here, we take our output from our ALU and send it to our display. Let me find a command right here. We have our ALU output buffer enabled right here. And then this is our display write command right here. We set to our display. On our final line, we halt the process. We stop the system clock. We insert the halt command on the very last line, and it should stop the system clock. Oops, oh, wrong one. 1, 2, 3, 4. 1, 2, 3, 4. Okay. That is not reading user input. It is going straight to the system. We run our code now, pushing the run button over here. It will start cycling through our code on here. Then it will give us our output on the display, which should be 2. As you can see, it has said 2 now. The program has stopped at the last line. You can also change the value on here to make it so it says 3 instead. We can change one of these lines here to be 2 instead of 1, does not matter which. Then we press the reboot button over here, which disables the run switch for a set amount of time until we can reset the program counter in a efficient amount of time. Now it will cycle through again. It will say 3. As you can see, it has successfully put in the value we wanted to put in here. And now we can turn it off and it's done. And let's go over the features that this computer has. If the world does not start lagging. Oops, so here is our 2-bit ALU. It can store value from 1 to 2 in register A and register B. Both halves are wired together as one wire and are controlled by the A and B controls right here, which select the registers that we need at the right time. Here is our outputs buffer. which will disable output when we're not using it, using subtractive comparators. This here is our equal to function, using a modified vertical XOR gate. Turn it to an XNOR gate using this torch on here to make it inverted. We set our address on here. If our value from the ALU equals an address value, it will give us a flag output that then can be used for command jumping. This will allow us to jump a function to a certain line if a certain condition is met, a certain value is met in the ALU. We can also check for an overflow if you wanted to, which will read an overflow. Wait, do I have that? No, I'm thinking of something else. I think it's a zero function actually I'm thinking of. Wait, is there another jumping function, or is it? I don't remember if I have the. Hang on, let me just check. Okay, it does not have the function I was thinking of. That is something else. It does not have. I thought it did. We can force the jump function manually, or we can jump if our ALU value equals a certain number. It has 16 instructions, and it has 4 banks of 2-bit RAM. A total of 1 byte of RAM. Well, technically 4 bytes if we were like counting it as a full byte, but it's a 2-bit system, so it's a little different. This here is our address controller. It's a little funny how it's designed though, but it works. Now, and over here is our display. Now, I actually took this design from a YouTuber named The Darkness 344. He made a tutorial on how to make a 4-bit computer, but I took some of his ideas and made it a little differently to make this thing. Oh, there's one more function I forgot to mention this. Each write operation is buffered by the system clock, which is it's a 30-tick clock. So every 3 seconds it steps to the next level, the next instruction. But each write operation is buffered by the system clock, which means you don't have to skip a line. If I want it buffered, I have to skip a line before writing it again. But the display is not clock buffered, unfortunately, so it cannot have that secure thing on it. I may plan to make a world download in the future, because I made a little book that talks all about it. It tells you how to program it. It's an example program and some wrong button, and some other notes on here and specifications. I am making another version of this that is a 1-bit system. I will make a video of that later. Then I'll make a 4-bit system and an 8-bit system. Be aware before I do that though. So I hope you enjoyed this little computer. If you want a tutorial, I may think about making one of those in the future. But I will see you. I will see you next time. And I hope you enjoyed, and thank you for watching. Goodbye.